Assume for the next three problems that a lump of clay hits head on with a stick in a complete inelastic collision. The clay is 14 kilograms and moves at 9 meters per second. The stick has a mass of 11 kilograms and a velocity of minus 5 meters per second. And the question one is, how many unknown final variables? Well, when we work 54, which we are going to work it, you'll be able to answer 53. So what we have here, it wants to know the final velocity. We have a lump of clay, and we just represent this clay with a box. And it hits head on with a stick, which is this box. And after they collide, they both move off together as one unit. And we want to know that velocity that they move off. So we start off as usual, P initial is equal to P final. And what we have here is, that's going to go to the clay, which is at 14 kilograms times 9 meters per second. And the stick, which is at minus 11 kilograms, that we picked that up from the velocity, times 5 meters per second. And that's going to equal, in the final, we're going to have the two stick together, so we're going to have 14 kilograms plus 11 kilograms times V final, and that's what we're solving for. So let's just put this in so V final is going to equal the stuff up here, 14 kilograms times 9 meters per second minus 11 kilograms times 5 meters per second. And we're going to divide it by 14 and 11, which is 25 kilograms. And we'll solve this one. (14 times 9) minus 11 times 5 divided by 25. So in this case, V final is equal to 2.84 meters per second. All you have to do is that's what to solve is M 1V1. In this case, it was minus M2 V2 is going to equal, they're going to be joined together, M1 plus M2, which is equal V final. And we solve for V final. That's what this was about. So the third part of this question here is question 55, and it says, how much kinetic energy is lost when the combination happens? And we have to know the change in kinetic energy is equal the kinetic energy final minus the kinetic energy initial. So with that, let's do it. So the kinetic energy final, we're going to say 1/2 and the mass final, we're just going to add, would be the complete lump, which was 25 kilograms. 25 kilograms times the velocity final. We calculated that to be 2.84, and that's squared, minus the kinetic energy initial. And what do we have for the initial? We had 1/2 the mass of the blob of clay, which was 14 kilograms, times its velocity, which was given to us at 9 meters per second, and we square that, and minus 1/2 the stick, which was 11 kilograms, times its velocity, which was -5 squared. By my calculations, that come out to be a minus 704.5 joules, which we always in the positive, which would be 704.5 joules. It's just a change in kinetic energy, the kinetic energy final that you come up, minus the kinetic energy initial. All right. You also may have, and probably will have, a question like this. Two pucks approach with equal and opposite speed. What is the dynamics of the collision? And so you got two pucks, and you know they're probably the same mass. That would be the first assumption I would make, is that they have the same mass. And they also approaching with equal and opposite speed. So you'd ask yourself, what kind of collision would two pucks make? And from there, you can go with whether the energy is conserved or not. And if you know those things, you can answer this question. 56. We have problem 57. We have two pucks. Puck A moving at 5 meters per second, is struck by puck B moving at 7 meters per second, what is the speed of puck A after the collision? Now, since we assume all the pucks are the same mass, when we look at M1 V1 plus M2 V2 is equal to M1 V1 final plus M2 V2 final. All the masses will cancel. And also, if you assume that it's an elastic collision, the masses will cancel in that also. So you'd have like 1/2 M V square initial plus 1/2 M2 V square initial is equal to 1/2 M V square final, that's for M1, and plus 1/2 M2 V square final for 2. And all your masses will cancel, the 1/2 will cancel. And you're left with just velocities. So the questions are going to go like, for this one, it's going to ask you questions like, it's going to ask you what is the speed of puck A after the collision? So you're going to have to decide whether you have enough information or does the two pucks A and B exchange speeds, or what happens in this case? So when you see this problem, you need to do a little digging. You probably had something like it in the homework, and decide, do you have enough information or can you compute the speed of A? You will see this problem. If you can't figure it out, email me and we'll go from there. Okay, you may get a problem like this. A Volkswagen Beetle hits a Mack truck head on. Which vehicle experiences the greatest force? Okay, so you will have to determine whether Newton's law apply, whether it's equal and opposite, or maybe look at what impulse is. You know, you have two impulses, J equals the change in momentum, and also you have J equals force times delta T. And we worked some problems in collision where we use this formula with the short time. Of course, this is jolt. This is impulse right here. So you need to figure out, and I'm sure you can, which vehicle experienced the greatest force, or are they the same? And you'll be able to answer that question. You will probably see a question like this, so don't take it lightly. 59, what we have is, how do you compute the angular momentum direction of a rotating disc? And you use the right-hand rule. In this case, I have it rotating this direction. Imagine just putting your hand in a direction and curl it in the way that it rotates, and your thumb will point in the direction of of the angular momentum vector. In this case, it's coming out of the page. So just orientate your hand when you see this question in the direction of the disc or whatever is rotating for the right hand rule, and then you can answer this question. For 60, you need to know the dynamics of what happens in an inelastic collision. And you know that in an inelastic collision, you have noise, you have things crumbling, and sometimes they, if it's completely inelastic, they join together. So what is conserved in inelastic collision? We know momentum is always conserved, but energy is not conserved in an inelastic collision. So knowing what is conserved, what happens to energy, and that sort of thing, when you ask a question about an inelastic collision, remember that energy is not conserved, but momentum is always conserved. So you should be able to answer a question like this just by knowing what an inelastic collision is. Okay, continue with our exam review. Problem 62. On exam, a cart mass 7 kilograms at speed 8 meters per second moves to the right, striking a cart of 4 kilograms and a speed of minus 5 meters per second. The two carts collide fully elastically and bounce back off of each other. What is the final speed of the first cart? First, I want you to look at two equations that we're going to have to use. In your book, page 238, if you're using edition 10 of RedSnake, you have this equation, which is V1 final equals M1 minus M2, M1 plus M2, V1 initial, and this one here, V2 final equals 2M1, M1 plus M2, V1 final. Now, you use either one of these two equations if one of the mass being struck is at rest. Now over here, you're going to have equation 9.67 is this part, and 9.68 is this part, and this equation here, if one of the balls or whatever you've been figuring out the velocity for is moving, if both are moving. This one over here, one is stationary, here both are moving. So it would behoove you to remember these equations, 9.75 and 9.76. Stationary, the two objects are moving, you add the whole thing. So it asks for what is the final speed of the first cart. So we'll use equation 9.75. It's important that you remember that. V1 final is going to equal to M1 minus M2 over M1 plus M2 plus 2M2 over M1 plus M2 times V2 initial, and this is times V M1 initial. Squeeze that in like that. So let's just plug in. M1 is 7 kilograms. Minus M2, which is 4 kilograms. All over 7 and 4 is 11 kilograms. And we'll multiply that by the initial speed, which is 8 meters per second, plus we got 2m2. M2 is 4 kilograms, so we'll just say 8 kilograms, divided by the total, 11 kilograms, and times V2 initial, which is a minus 5. So what we have, V1F is equal to 7 minus 4 is 3 over 11 times 8 plus 8 over 11 times minus 5. You have to make sure you put your signs in. So 8 times 3 is 24 over 11 plus, that's a minus 40 over 11. So when we do the math here, we're going to have a minus 40 from 24 is going to give us a minus 16 over 11, which is going to equal, so we have a minus 16 divided by 11. Let's say minus 1.45 meters per second. All right, 63 says for the same setup, but they want the velocity of V2 of the other cart. So now just remembering these two equations, even though it shows you how to set up, how to derive the equations, but it gets a little tricky with this algebra here. You can see over here, I went to see a professor in the math department to see if we could do the algebra a little easier, and he decided to come up with some things that I believe made it more complex. Now we got A's and B's and C's, so let's just stick with learning these two equations. In this case, it wants this equation. And they're kind of easy to remember. Remember, if one of the objects is stationary, you're just going to have this. So for 63, we know that the initial, we got 7 kilograms, moving at 8 meters per second. That's initial. And we have 4 kilograms at minus 5 meters per second, and that's initial. So this is what we're going to do. We're just going to use this formula here for the second. V2F equal 2 times M1. So that's 2 times 7 kilograms. So always divide it by the total, 7 and 4, which is 11, times the initial speed of M1, which is 8, plus M2 minus M1. M2 is 4, minus M1, which is 7, divided by 11, times the initial speed of V2, which is minus 5. Now, as you say, V2, F is equal to 14 over 11 times 8 plus a minus 3 over 11 times a minus 5. So we're going to get 8 times 14 divided by 11. Which is going to be equal to 10.18 plus, we're going to get a 15 divided by 11, which is 1.36. And when we add those, we get an answer of positive 11.54 meters per second. Okay, with our review, and this will probably be a problem on your test. Now, what you need to do, just make sure you understand the concept. And the question is the kinetic energy, potential energy, angular momentum, linear momentum, all constant in a Earth-Moon orbital system? So that's going to be a multiple choice question. So let me just tell you this. The angular momentum is constant. So that you don't have to worry about that. But think about the potential energy and the kinetic energy. Okay, the kinetic energy would be, if we were expressing it, it would equal 1/2 I omega. You know, omega is constant. You know, I is constant. So you conclude that the kinetic energy is constant. And also the potential energy would be expressed as G, M mass of the Earth, just over R. We'd assume that R doesn't vary very much. Newton's constant is a constant for sure. The mass of the Earth is a constant, and the mass of the Moon is a constant. So we'd assume that the kinetic energy and potential energy are constant. So what does that leave you with? Linear momentum. Is that constant? Well, I'm sure you guys have been working pretty hard to getting ready for the exam. linear momentum is not constant. So if you remember that, you'll be able to answer that question when you see it in a different form on the exam. Test review, question 8. We have a mass of M equals 62 kilograms is attached to a spring of K, spring constant, equals 1,400 Newton meters. If it's pulled out to a position stretching a distance of 0.59 meters before being released, how fast is the mass moving after returning the distance back to the center? And we're going to say energy in the system is going to equal the kinetic energy plus the potential energy. Now we're given that the total energy in the system when it's first stretched is going to be 1/2 times the spring constant, which is 1,400, times the distance that is stretched, which is 0.59 meters, and this is squared, which is going to equal the kinetic energy, and once you release it, 1/2, and the weighs 6.2 kilograms times 6.2 kilograms V squared. That's what we're looking for. Plus the potential energy, when it comes back 1/2 of the distance, it's going to be 1/2 times the spring constant again, which is 1,400, times 0.59 divided by 2, coming back half of the distance, and that's squared. So we have 700 times 0.59 squared, which is going to be 243.67. And we're going to have 0.5 times 6.2, which is going to be 3.1 V squared, plus 700 times 0.59 divided by 2 squared. That's going to give me 60.92. And we'll just carry this out a little bit more. We have 3.1 V squared, that's what we're looking for. It's equal to 243.67 minus 60.92. So we have, we'll just subtract this. 243.67 minus 60.92 And we have 182.75 on this side and 31 v squared. So v squared is going to equal 182.75 divided by 3.1, which equals, we divide that by 3.1, 58.95. So V is going to equal the square root of 58.95, which is going to equal 7.68 meters per second. All right, continue with the review. We have a spring mass system, has a max stretching distance of 0.5 meters from its rest to 0.5, and a max speed of 7 meters per second. So when it comes back here, it's going to, from here to here, it's going to be at 7 meters per second. How much time does it take to complete a full cycle and return to the configuration it started? Okay, so it gives you a hint to compute omega. And once you find omega, you can find the period. And so this is what we know. We know that V is equal to omega times x. That's the stretching distance. So all you have to do is say omega is equal to V divided by x. And in this case, it's 7 meters per second divided by the stretch distance, which is 0.5 meters. And that's going to give you 7 divided by 0.5. Going to give you 14. That was obvious. And this is in ohmadians. Now we're in radians. When you that's what omega is in radians. So now for the period t, it's just simply 2 pi over omega, which is going to be 6.28 divided by 14 rads and the period is going to be 0.45 seconds. Just remember, velocity is omega times the stretch distance. Solve for omega. And the period is 2 pi over omega. And that should be all you have to do for that problem.